Tuning is a weird, wacky, and wonderful world. I'm the classical nerd, and today we're talking about what exactly a cent is, aside from a useless piece of currency that costs multiple cents to mint. To tackle this question, we're going to need to ask ourselves exactly what these two values are intended to measure. Hertz, named after Heinrich Hertz, and not to be confused with the rental car company of the same name, measures in purely objective terms the number of cycles per second. So when looking at a pitch, this tells us how many compressions and decompressions, or rarefactions, there are in the air every single second. If you cram 440 of these into the span of a second, you get the A above middle C, the one that orchestras tune to. Hertz aren't super useful in musical terms because they're so deeply scientific in nature. There's no one-to-one relationship between a value in Hertz and some kind of musical value that we would understand. It's not that you can just add a certain number of Hertz and then get a certain pitch above. You have to multiply the value in Hertz by 2 in order to get the next octave up. So to get an octave above this A, you need to double the value to 880. In order to get the octave below, it halves to 220. Middle C then becomes 261.625565 Hertz. Multiplying and dividing by the 12th root of 2 gives you the value in Hertz from one note to any other note. That's the value in Hertz between two consecutive half steps. But again, it's multiplying. You're not adding anything, which is why it's kind of hard to get your head around if you're not used to logarithmic scales. The cent measures something completely different and has nothing to do with pitch values in terms of Hertz. The cent slices the half step into a whopping 100 bits, and a 1 cent difference is impossible to discern. The cent's main use is for extreme fine tuning, or to compare the size of similar intervals in otherwise different tuning systems. So you can see exactly how small or wide, say, a pure major third is when compared to a major third in an equal tempered scale or some other well-tempered scale. Because pitch is logarithmic, this too is also logarithmic, but in a little different way than the Hertz is logarithmic. So let's look at the standard modern piano keyboard. The lowest C is 32.70 Hertz, and the C sharp right above it is 34.65 Hertz, which is 1.95 Hertz difference, which means that you don't need an even full 2 extra cycles per second of compressions and rarefactions to get from one note to the note right above it. The difference in Hertz is extremely minuscule. This means that on average, the distance of 1 cent between these two notes works out to about 0.02 Hertz each. So now let's compare the two highest notes on the keyboard instead. B7 is 3951.07 Hertz, and C8 is 4186.01. Which means that, because of the logarithmic nature of these tones, there are now 234.94 Hertz between consecutive notes, which is a major difference from the 1.95 we saw earlier. Again, this is the same exact interval we looked at a second ago. Second. This means that the average value in cents between these two tones on the highest register of the piano keyboard works out to 2.3. Not only is this orders of magnitude larger than the average size of cents on the lowest end of the keyboard, but this means that the distance between 1 cent and the next on the highest end of the keyboard is a larger value in Hertz than the difference of a half step on the lowest end. One we can hear, the other we can't. Yet to our ears, 50 cents just still sounds the same.